My name is Julia Silye, and I am a data scientist and software engineer at our studio. And today in this video, we're going to be talking about how to use tidymodels for unsupervised machine learning. Tidymodels is great for predictive modeling, for supervised machine learning, but also it can be used for unsupervised machine learning. We're going to use this week's Tidy Tuesday dataset that is all about cocktails and cocktail recipes. And we're going to show how to implement two different kinds of unsupervised dimensionality reduction algorithms using packages from the tidymodels framework. First, we're going to show how to do principal component analysis, and then we're going to show how to implement a UMAP, which is another way to do dimensionality reduction. Let's get started.
Here we are. Let's use tidymodels to explore this data set of cocktail recipes. Let's paste this here. So there were in this week's Tidy Tuesday data set, there are two data sets of cocktail recipes, and I'm using this one called Boston cocktails. And so let's explore and see what we have here. So we've got all these ingredients here, and let's take a look and see what we have. So one thing, so we can see that some of the most common things in this data set are things like gin and lemon juice and simple syrup, lime juice. Let's notice a few things here that we probably are going to want to take care of in some data cleaning. There's inconsistent, first of all, capitalization. There's like juice is capitalized, here, but not here. There's also inconsistent use of some things like the juices, for example. So we have fresh lemon juice here and juice of a lemon here and lemon juice here. So we're probably going to want to handle that in a certain way. And then also notice that we have apricot flavored brandy with a hyphen here and without a hyphen here. So that's something we're going to want to handle as well. What are some other things? I bet so the grapefruit juice, orange juice, lime, lemon. These are things here. Look, lime juice again with capitalized here. So these are things we're going to want to all handle in how we. Oh, and then look here. There's maraschino and maraschino liqueur, which I'm 95% sure are the same thing. I'm not the world's biggest expert on cocktails, but I'm pretty sure those are the same things. What other? Oh, light cream if desired. And then I think I just saw light cream somewhere else. Light cream. So these are some of the kinds of things we're going to want to take care of. So let's start making a cleaned up version here. So Boston cocktails. I'm just going to be doing this all to the same variable here. So first, let's change it all to lowercase. Then let's replace all of the incidences of dashes with spaces. Let's remove some of those things that we had around. So string remove. So we'll say ingredient here, and let's remove, we'll say space liqueur and something else, space if desired. So this is going to take care of a lot of stuff already. What else do we have here? You know, for the kind of purposes of what we're going to do here, which, like I said in the introduction, is going to be looking to use some unsupervised machine learning algorithms for you can use either for EDA or for dimensionality reduction to go into modeling. I am not, you know what, I'm not sure that the Angostura bitters are that different from bitters, which are that different from orange bitters. I'm just going to call it all bitters. So the next thing that we're going to do here is I'm going to start, ingredient. I'm going to start renaming some things. I'm going to use case when. Yeah, I could also do this with like a join, but I'm going to do it with case when for now. So when I see anything like bitters in the this will be orange bitters, regular bitters, any kind of bitters. I'm just going to call this new thing bitters. Now, it's not good that I have that first, because then orange bitters will go to bitters, and then if I have, say, orange juice afterwards, it will go to orange juice. And then let's do this for all those citrus juices. So there was orange, lemon, lime, grapefruit, lemon, lime, grapefruit. Could have maybe made a little function for that. Perhaps that would have been better. True ingredient, like so. All right, so let's see what we have there. And now if I count ingredient, how cleaned up did that get? Let's take a look. That's looking pretty good. So the maraschinos got put together. So we have all the apricot flavored brandies together. Boy, I don't know that I've ever had apricot flavored brandy. This is looking good. This is good. This is from this is I think the brand that this came from, so it's kind of funny that we see that in here, but I think that's fine. Oh, this didn't work. Replace string remove. Let's see if we can get that. But it did. Oh, I think that I'd have to do it separately. Or this or isn't gonna work, I think. That's fine. That's fine. Okay. Let's just count ingredient sort equals true, and look one more time. Yeah, so that's fine. This is good. This is certainly more cleaned up than it was, so that is great. All right, now let's think about the measures. So a lot of these things are measured in ounces, but boy, I hope that you have never had a cocktail with an ounce of bitters in it. Or for goodness sake, I hope you've never had a cocktail with 2 ounces of bitters in it. You know, the rest of these look okay. Like I believe the rest of it, right? Seems very reasonable. You know, I bet there was an error, and that it's supposed to be dashes, like 2 dashes of bitters, 1 dash of bitters for a cocktail. Because the rest of this seems very reasonable. But, I mean, there's just no way. There's just, that's like the whole bottle of bitters. And that would be undrinkable. We would not wish that upon our worst enemies, right? None of us would make such a cocktail. All right, what are we going to do? Let's just keep going with this massive mutate statement. Why not? All right, measure. So, I'm going to use, what am I going to do? How about another case when? I love case when. Okay, so when I detect in the ingredient bitters, then I'm going to replace any string replace. I'm going to replace any string in the measure ounces at the end with dash. And the rest of the time, it's just going to stay measure. Let's see how that works. So let's look at ingredient. Let's count. Let's count ingredient measure. Sort equals true. All right, that's much better. A dash of bitters. So I'm making an assumption here about the kind of error that happened in the data generating process, but I think it's a reasonable assumption. Certainly it's going to end up, I'm going to end up with a better unsupervised and better results for my unsupervised modeling using this assumption, this correction, than if I just press forward assuming there were 2 ounces of bitters in these cocktails. So that's what we're going to do. That looks good. So we're going to do that. Okay, so I've made this correction to the measures. The next thing is that I do actually want a number out of here. So I'm going to replace these fractions that sometimes have a space in front of them with a numerical like with a 0.5. So I'm going to say measure string replace measure. Okay, so if I'm going to replace space comma or question mark half with 0.5. Not, that's wrong with this. So it's going to say this does not have to be here and this does with half. So let's see if that works. And let me look at this. Count ingredient measure sort equals true. Okay, that worked. Half an ounce, 1.5 ounce. That worked. I think there were I saw at least 3/4 and 1/4. So let's do those. 3/4, 1/4, 3/4, 1/4, like so. And the next thing I'm going to do is I'm going to make a new column called measure number. I'm going to use parse number to get the number out from the measure, like so. And so you can see what this does. Let's say select measure and measure number. So parse number is so useful. I use it all the time in so many different contexts. Do notice that it didn't work for all of them, so I'm probably gonna have to filter out these NA values when it didn't work for some proportion of these thousands of rows that I have. So I'm gonna have to filter those out that I don't have anymore. But for these though that we can see it worked, for many of them it worked. We can look and scroll down and see all these ones for which it did work. Remember, some of these are dashes now though, and so for the ones that are dashes, we whoops, this is still actually in this. So measure number So let's use if else. So if in measure I detect a dash at the end, then measure number, I think, I don't know, like divided by 50. How many how many dashes are there in an ounce? I think 50. And then if not, we will just keep measure number like this. Okay. This is looking good. Okay, so let's see. How many ingredients do I have at this point? Count ingredient. 440. That is too many. So let's because I'm gonna make a wide shaped data frame from this long and narrow tidy data frame. And that's going to be too many here. So let's add a column and let's filter. Let's say we're going to keep ones that appear at least 20 times. Let's see. Let's see how many that leaves us with. 30. Let's what if we go to 15? Count ingredient. 40. I think that's good. 40. So we're going to have 40 columns in our data set at the end, and it will have things like bitters and Blanco tequila and these different kinds of whiskey and whatnot. Those are going to be our columns. Okay. The next thing I think we are going to need to have to do is that when we did this with like orange, lemon, and lemon juice, things might be in here twice now, because we might have like a lemon, say like a lemon slice and lemon juice. So I better distinct, let's say row ID, which is one of these columns that we had in here. Row ID here. So let's distinct row ID and ingredient, but keep everything. All right, there we go. Data cleaning. Let's call this cocktails parsed, like so. Cocktails parsed. And this, I think, is clean enough. Clean enough for our purposes. All right, so this is now cleaned, and I do almost always clean my data in a tidy format like this, but when it's time to do modeling, I almost reshape my data into a wide format. So let's do this. Let's take our let's select off. We no longer want that ingredient number. We no longer want that row ID, I don't think. And I don't need that measure that is the that string version, because I only want the measure number. So I'm going to keep the name and the category around. These are going to be information. They're not numerical information that's going to be part of the model, but they're information I want to know, the name of the cocktail. But the things that are going to go, this is going to be the name of the new column, and this is going to be the value that goes into the column. So let's look at, so we're going to use pivot wider from tidyr to do this. So the names come from the ingredient and the values come from the measure number, like this. So if we do this, we end up with a very wide data frame. Notice, there's NAs because, not every cocktail has every ingredient in it. And so here, we don't want those values. We don't want those values to be NA. We want those values to be 0. So we will make those values 0 like this. And then I don't want these spaces. So I'm going to use janitor clean name so that I have beautiful snake case clean names, and then I am going to do NA omit here so that I get rid of things that happen because of my parsing failures, so that I don't have anything with NAs here. I could have maybe done that here actually and kept some more cocktails around. Yeah, that's actually a better idea. Let's do it up there. Okay, so let's call this cocktails DF. And this is what we're using for our modeling, is right here. The first, we're going to do two kinds of unsupervised machine learning algorithms for dimensionality reduction. So we've got this, high-ish set of dimensions. It's like 40 set of dimensions, and we want to project and picture this like 40-dimensional space. We all love it when people say things like that. Picture a 40-dimensional space, right? And the cocktails, each one of these cocktails is somewhere in this 40-dimensional space. And we want to use fancy math of some kind to build these low-dimensional spaces where we can visualize where the cocktails are in these low-dimensional spaces, and then we could use it either for modeling or for understanding more deeply about this data set of cocktails. So we're going to show about two approaches to do this using tidymodels. So let's load tidymodels. And one thing I love so much about this particular analysis is that we're going to use recipes on the cocktail recipes. It's perfect. So every time I think we've done recipes before, we've built a recipe for data preprocessing, we've had an outcome. And here we don't have an outcome. This is just unsupervised, machine learning. And so we write our formula like this, and we say data equals cocktails DF. So this is how we start our recipe here, our recipe for our cocktail recipes. The first thing I'm going to do is update the role, because I have these two variables that I want to keep in my data set because they're going to be helpful later on, but they are not predictors. They're not data that I want to go into the unsupervised machine learning algorithm. So the next thing I'm going to do is step normalize, and I'm going to normalize all my predictors, because the next thing that I need to do, which is step PCA for principal component analysis, needs to have the data normalized. So this what step normalize does is it centers and scales all of the different variables, and then this performs the principal component analysis. So let's call this PCA recipe. So what I've done right here is I've just defined what I am going to do. I have not yet actually done anything yet. So the first step in a recipe is to set it up, to say, here are the steps of my recipe. The next thing that I do is that I prep a recipe. So the prepping of the recipe actually goes to the data, which here is this cocktail recipe, and it actually estimates all the values that need to be known from that data. So now some values were computed. Here, no values were computed. Here, some values were computed. So you can kind of tell some difference here. Here it gave fairly neutral, some fairly neutral things were printed out, and here it actually said, yes, it is trained. I know the name of the names of the columns now. It is done. I have actually done the thing you've asked me to do. So with principal component analysis, we can do a couple of things. One thing that we can do is we can tidy it. There are actually several, we could actually tidy this first step too, which is not that interesting because it's just centering and scaling. It would say, what's the mean? And then we could actually get out the standard deviation as well. What we want to do is we want to tidy the tidied PCA. We want to tidy the principal component analysis step. So we say what this gives us is for every principal component that we computed, what is the value for this term, for light rum, for lemon juice, for lime juice, for sweet vermouth for that component. So we have all these values. Let's make a visualization for some of them. So let's look at, say, let's say the first 5. Let's look at the first 5 components. And let's look at everything. Let's look at it all. So we're going to have to say fact in order, or fact in order component, so they go in order. And then let's do it. Let's put the value on the x-axis, the terms on the y-axis, and let's color them. And let's make a bar chart. And what we're doing here is we are going to make like a different little small multiple for each of the principal components. And let's put them all together here. Okay. So let's look at this and zoom in a lot so we can see here. So what we have here on that y-axis are all the 40 different ingredients that we're looking at, and then what the bars are is how much do they contribute to each of these principal components. So let's look at PC1. So you can see here it just happens that powdered sugar and simple syrup are right next to each other, and notice they're in the opposite directions. So that means that cocktail recipes tend to either have powdered sugar or have simple syrup. They tend not to have both, right? Which makes sense. You don't want both of those things in your cocktail. It will be way too sweet. Notice we can start to see what are some of the things that go together over here on this side. Gin, egg yolks, egg white, powdered sugar. So these are like the fizzy egg drinks. The things that are on this side are like simple syrup, lime juice, rum, tequila. So this is like a limey, sweet tequila rum side. If we go over here to PC2, on this side, all the sweet things are together on this side. Not all of them, but there's like a lot of sweet things over here. And what's biggest on the other side is sweet vermouth and dry vermouth. So these are like the vermouth drinks versus sweeter drinks. And then we can kind of walk on down and see, PC5, it looks like is dominated by, is that cream, and I don't know what the citrus flavored vodka. I don't even know. Who even knows, right? Okay, so that is looking at like kind of a big view. It is probably better to zoom in. Let's here, I'm gonna copy that. Except let's go down just to 4, and let's just take that is not what I wanted. Let's group by component, and let's take the top 8 by absolute value for each component. So what contributes the most to these 4 components here? And let us, we will make a plot like this. So we'll say the absolute value the terms, and then let's this time color them as to whether they are, if they move in the positive direction or the negative direction. And we'll say geom call, and we will do the same thing here, except I think we'll have to do scales equals free y like that. And let's see what we've got there. All right, that is looking interesting. So we're going to say labs y equals null, and then on that fill, you know, we would say like positive, you know, like does it contribute in the positive direction or not. Let's reorder these. I think since we have since these double up with each other, we will use reorder within. So here we'll go mutate terms equals reorder within. So we're reordering terms by absolute value within component, like that. And then we have to add scale y reordered, like that. You have to add those two things to get it to reorder. Okay, now that looks pretty good. Okay, so this helps us for these first four components understand what contributes to them. So remember, so for principal components, the first one explains the most variation in these cocktail recipes. So whether something uses powdered sugar versus simple syrup, whether something is a powdered sugar eggy gin drink or is a simple syrup lime tequila drink. That is what explains the biggest difference. PC2 is something a vermouth drink, or is it a powdered sugar, lemony, sweet, perhaps eggy drink? So this is that's what these that's what principal component analysis does. That's what it is able to do. We can make a pretty nice visualization. We can juice this. This is all so perfect that it's like I can't even believe it. We can juice the prepped recipe and get the data back out. So in this case, what that does is it gives us the name and the category of the cocktails, plus where are these cocktails in the five principal components that we trained. We could have gotten more by changing when we, like in here, we could have given an argument and gotten more than 5, but we just use the default, so we got 5. So for each of these cocktails, where are they in the new 5-dimensional space? We had a 4D-dimensional space, and we projected down to a 5-dimensional space. And on any given row, what these numbers are is they tell us where are they in the 5-dimensional space. So we juice the prepped recipe to get that information out, and now we can say, okay, PC1, PC2, and make some points. You know, we can give them some nice characteristics here, and here we go. Okay, looking good so far. This shape is super interesting, right? This very triangle-y shape. Let's put in here in the points, let's put in the color. Color equals category. So that's this category here that came with this data, this Mr. Boston data set here. Okay, so something about, so what we have learned from the principal component analysis is related to the categories that this data came to us with, which perhaps isn't shocking, but these cocktail classics, which are very numerous, are all over here this was like the eggy, fizzy area. This up here was the vermouth area. And then over here was like the lime simple syrup tequila area over here. So, we can actually put the names onto this by saying label equals name, and then adding adding a geom text layer. So let's say check overlap equals true, so things don't print over each other, and then let's say family this, so that it matches. We don't have two sets of fonts in the same plot. Okay, good. All right, let's just clean that up a little bit. Let's say labs color equals null, and let's also here let's say like the horizontal justification, let's make it inward so that it does not try to print off of the side. And then let's make this big so we can see it. All right. Okay, great. So let's think about this shape again. So we've got all these things called things like fizz over here, because remember, this is the side that's eggs, powdered sugar, gin, and notice these are a lot of these are called like cocktail classics over here. If we go up this direction, this is up into the has vermouth section, either sweet or dry, and then we go down this direction. This is the direction that is lime juice and simple syrup, so that moves things over this direction. So this PC1 and PC2, these are the two principal components that explain the most variation in ingredients in this data set of cocktail recipes. If we're interested in seeing how it changes, if we go to a different, let me stretch this up a bit, and we can, for example, change this very easily to PC3 and see how the shape changes. Notice it really changes a lot because we're taking the high dimensional cloud of cocktail recipes and we're projecting it in a different direction. And now we're looking at we're looking at along a different axis. So this is what principal component analysis does. It lets us learn this kind of information about it, and it can be a useful. We can use it to learn, and then also it can be useful input into another kind of modeling procedure that we want to do. The next thing that we're going to do here is we implement it similarly, but it turns out it's really quite different mathematically. We're going to look at a different unsupervised machine learning algorithm for dimensionality reduction called UMAP. So UMAP does not use the same kind of math. It uses like here, let me show you a little bit. So there's a whole nother package called embed, which provides recipe steps for embeddings. And what we're going to do here is we're going to change this to UMAP recipe, UMAP prep, and we are going to use step UMAP. So UMAP is based on topology, on projecting into these lower dimensional space, but on these like manifold approximations. There's a really nice link in here. Where is it? Down here, about how UMAP works. I think it's a really nice like explanation that walks through the geometry of how the topological stuff works. And you're gonna see when we get to these results, really get a sense of how this works. So here's what we're gonna do. Ta-da! Now we're doing UMAP. So one of the really powerful benefits of the tidymodels approach for unsupervised or supervised modeling is how flexible the user interface is for being able to try lots of different things. So I'm just going to copy and paste this visualization that I made here. So instead of juicing the prepped PCA prep, I'm going to juice the UMAP output. So the default here is to get out two components, and so that's all I have. You can change it to get out more. So I'm just going to put these in here. I'm going to keep everything else the same, and we're going to look at our result here, and you're going to see, we're going to examine just how different it is. So instead of smooth distributions, we have this really clumpy distribution. Notice how things that are, say, tequila are all really close together. Things that are rum are all very close together. Like here's the vodka section. Although it looks like we have some things out that are further away. They must involve some other kinds of ingredients here. So this visualization is, first of all, helps us see what kinds of drinks are distinguishable from the others based on the ingredients that we have in this data set. It also really helps us understand what is it that UMAP is doing that is different from PCA. UMAP is finding these, the way that UMAP uses its like topological map, it is finding these things that are very close together and like clumping them and finding these things, which is very different from what PCA is doing. And depending on the kind of what you want to learn from your data or the kind of modeling thing that you want to do, it's really great to be able to have both of these things in your toolkit.
All right, we did it. And there are several big takeaways from this video. The first is, don't ever put 2 ounces of bitters in your cocktail, no matter what any recipe says. Another big takeaway I think you should take from this video is the tidymodels framework allows you to flexibly and fluently switch between different kinds of algorithms that you might want to try, whether that is an unsupervised algorithm or a supervised machine learning algorithm. So I hope that was helpful, and I will see you next time.